Hello everyone, welcome to chemistry class. This is lecture 3 of the online class series. In the last class we had discussed the topics of periodicity, orbits and valency. In this class onwards, we will start discussing the periodic properties and their variations in the periodic table. Before we begin our class, let us make sure that you have been thorough with the topic of orbits and thereby valency. If there is any doubt pertaining to those topics, I expect you to watch and revise the last or the previous lecture. Let us come to our today's topic. As we discussed in the last class regarding the periodic properties, what are periodic properties? The question arises, we had discussed this in the last class. Periodic properties are those properties which reappear at regular intervals or which show a gradual variation in the periodic table. There are the following periodic tables which we will be discussing in our syllabus. They have been mentioned clearly. They are 6 in number as are shown over here. One by one we shall discuss them in detail, and the variations shown by these periodic properties will also be discussed. In today's class we shall be discussing atomic size or radius, metallic character and the non-metallic character, and thereby the trends followed or observed in the periodic table pertaining to these physical properties. The first periodic property that we shall be discussing today is atomic radius. Here the question arises, what is atomic radius? First we'll see the definition, and then followed by that we will see the trends observed regarding this property in the periodic table. So let us see the definition. Here two definitions are mentioned along with the proper diagram. The diagrams I have taken for reference from your class textbook. You can refer to these in your class textbook. First definition follows as, atomic radius is the distance between the center of the nucleus and its outermost shell. You see the diagram given over here, and it shows the atomic radius. It is actually the distance from the center, exactly center of the nucleus, to the outermost shell of that atom. This is called as atomic radius. Another definition shows it is half the internuclear distance in case of combining atom. The first definition was for single atom. First one was for single atom. But in case two atoms are joined together, then the second definition is given as atomic radius is half the internuclear distance. Internuclear distance means when two atoms are joining. Here two atoms are joining together, overlapping together, and whatever the distance is between these, between the nucleuses, individual nuclei of these atoms, whatever the distance, its half is called as atomic radii. So these two definitions are for atomic radius. Now this atomic radius depends on various factors. First one is number of shell, second one is nuclear charge. Number of shell, as you can see in the above diagram given over here, as the number of shells are increasing, the atom size will keep on increasing. So we can say if more shells are there, then we can have more atomic radius. More shells give more atomic radius. Next one is nuclear charge. Nuclear charge is equal to the number of protons. Let us read this first. Nuclear charge. Nuclear charge is the positive charge in the nucleus of an atom. Whatever is the number of positive charge or the number of protons, that is equal to the nuclear charge. For example, sodium for example is having the atomic number 11. That means it is having 11 protons. Atomic number definition earlier already we have gone through. So if sodium is having 11 protons, that is the nuclear charge for that particular atom. Similarly for hydrogen, it is having 1 proton, so that will be its nuclear charge. So that is the nuclear charge. So whatever is the positive charge is called as the nuclear charge for that particular atom. Now how does it affect the atomic radius? So here it is mentioned here, an increase in the nuclear charge decreases the size of atom because electrons are attracted by the nucleus with greater force. So what they are trying to say here is, if we are having more positive charge is there in the center of the atom, then that center of the atom or that nucleus will attract, it will be able to attract more negative charge. Opposite charges are attracting. That is a common law. You already know that. So if more positive charge will be there, then easily that more positive charge will attract more number of or more amount of negative charge. In other words, we can say that if the nuclear charge is higher in a particular atom, then its electrons are attracted with a greater force. More number of protons easily attract more number of electrons towards the center of the atom. As a result, what will happen? As a result, the atomic size will decrease because the center of the atom containing the more number of protons is easily able to attract the electrons from the outermost or from the shells of the atom. Let us have a look at the trends in the atomic size in the periodic table. One by one, we'll see both the points. First one is down the group, second is across the period. So down the group, when we go down the group, the size of the atom increases. The atomic size increases as we move downwards in a particular group. The reason being the addition of new and new shells. As we move downwards in a particular group, what is happening is number of shells are increasing. For this as an example, this table I've taken for reference from our textbook. You can refer to in your class textbook. Now you see here hydrogen, lithium, sodium, potassium, rubidium and cesium. All these belong to group number 1, and the atomic size you can observe here is regularly increasing because of the addition of more and more shells. After every element as you move downward, single orbit or shell is added to the atomic structure. You can refer to the electronic configuration. Also you can see the addition of shells is there, as a result of which the atomic size is increasing. So as you go down the group, the atomic size increases. Coming to the second trend in atomic sizes across the period. As you go left to right in the periodic table across a period, the atomic size decreases. Yes, the atomic radius or size decreases left to right in a period. The reason being because the nuclear charge is increasing. As a result, the outermost electrons, that is the valence electrons, come closer to the center of the atom because number of shells is not changing across the period. What is happening here, you see in the given table here, we have taken the particular period from the periodic table. This is lithium, beryllium and so on. Now you observe here the atomic size is reducing. You may see there all the atoms given in the table are having 2 shells. That is, the number of shells is not changing. The number of shells is same. On the other side, although the number of shells is same, the protons or the nuclear charge is increasing as the atomic number is increasing. 3, 4, 5, 6, 7, 8 and so on. So the atomic number or the number of protons is increasing. As a result, the nucleus contains more positive charge or more nuclear charge. Nuclear charge will become more and more stronger as we go from left to right in the periodic table. Although the shells are constant, the number of shells is not changing. As a result, what is happening? The outermost electrons are easily attracted by the high nuclear charge. In case of lithium, only 3 positive charge. The nuclear charge is plus 3 only. In case of fluorine, it is having 9. The atomic number is 9 here. So that is why fluorine containing 9 positive charge and lithium is containing 3 positive charge. So it is obvious that fluorine with 9 positive charge will be easily or more effectively hold the electrons compared to lithium containing 3 positive charge or 3 nuclear charge. Therefore, fluorine will have a smaller size compared to that of lithium. So, in the end, we may conclude that the atomic radius decreases as we go from left to right in the particular period. Observing this table, a question may arise with regard to the noble gases. You may be observing here the atomic size is decreasing as we are going left to right, but suddenly just after fluorine, neon is shown bigger or larger in size as compared to fluorine. Neon is bigger than fluorine. Why is it so? That is due to its octet is complete. Because its octet or the outermost shell is complete, it is having maximum number of electrons in the outermost orbit. As a result, electronic repulsions are maximum and the nuclear pull or the nuclear charge is not able to overcome. As a result, the noble gases or neon in this case is having the atomic size larger than fluorine, oxygen and so on in this particular period. Having been discussed about the atomic radius, we'll now see some of the exceptions that are seen with regard to atomic radius. The first one, atoms of inert gases are bigger than the halogens. Just now we have seen with the help of the example how neon is having atomic size bigger than that of fluorine. So the reasons are here. Already I have explained that. The second point, I'll zoom in there. The second point is, or exceptional cases, cation is smaller than the parent atom. Always the cation is smaller. Why is it so? Because the cation, that is the positive ion, it is formed by the loss of electron. As a result, because electrons are lost, the number of protons become more than the electrons. The protons are more than the electrons. As a result, we can say the positive charge is more than the negative charge in that particular atom. Hence, the electrons are more strongly attracted by the nucleus. Just for an example, to make it more clear, we'll take example of sodium. Sodium normal atom contains 11 protons and 11 electrons. If it loses one electron, it will still have 11 positive charge, but it has lost one electron, then it will have 10 electrons. Now, if we compare here, in the normal atom, 11 protons are balancing or attracting 11 electrons. But in the positive ion, the same number of protons, that is 11, is attracting 10 electrons. Here, the 11 protons are attracting different number of electrons. So, as a result, in case of sodium ion or cation, less number of electrons are there. That is why they can be more attracted towards the center of the nucleus. Hence, the atomic size is reducing. As a result, we will say the cation is smaller than the parent atom. Any cation is smaller than its parent atom. The next one is anion. There also the similar concept will apply with regard to the number of protons and electrons. Always the anion is larger because cation is smaller. Here, anion is larger than the parent atom. Anion is negative ion. For example, we will see one example of chlorine atom. Chlorine, for example, is having 17 atomic number. That is, it is having 17 protons and 17 electrons. It loses one electron. Sorry, it gains one electron. This is negative ion. It gains one electron and hence it will have 18 electrons. But the proton number is not changing. As a result, now these 17 protons which were earlier balancing 17 electrons, they have to attract 18 electrons. They have to attract more electrons. As a result, what will happen? The nuclear effect, the effect of the nuclear charge will be reduced because now they have to attract more number of electrons. As a result, what will happen? The nuclear pull is less effective and hence the anion is larger than the parent atom. Coming to the next exception here, the size of the isoelectronic ions. Now what are isoelectronic ions? These are the ions which are having the same number of electrons. They can be of different elements having in the form of ions, but they all are having equal number of electrons. How is it possible? For that, for an example, we'll see one example over here. For example, magnesium forms Mg2 plus ion. Similarly, sodium forms Na plus ion. You can refer to the example in the textbook as well. Magnesium is having atomic number 12. Sodium is having atomic number 11. Now because it is 2 plus ion is formed there, that is, it has lost 2 electrons. So ultimately it will have 10 electrons because it has lost 2 electrons. Similarly, sodium having 11 electron, it loses 1 electron to form the sodium ion. As a result, it is also having 10 electrons. So both magnesium 2 plus as well as sodium plus is having 10 electrons each. That is why they are called isoelectronic ions. Now here, although the electron number is same, the number of proton is different. Mg2 plus, the example that we took, magnesium 2 plus. Here the atomic number or the proton number was same. Electrons were 10 in number, but protons are 10. Protons are 12. In case of sodium also, protons are 11 only and electrons are 10. Electrons are same, but protons are different. This proton number is different. They are not same. So the same number of electrons are there, but protons are different. Now here, if we compare, in case of magnesium now, 12 protons are managed, or they are attracting 10 electrons. In the case of sodium, 11 protons are attracting 10 electrons. So different number of protons are attracting the same number of electrons. As a result, the nuclear pole will be different, and ultimately it will depend upon the nuclear charge. The greater the nuclear charge, the smaller is the atomic size. So whatever ion is having more number of protons, it will attract the electrons more easily. As a result, magnesium in that case, in our example, will have a smaller size compared to sodium atom. These are all the different exceptions regarding the atomic size.